Hi, and welcome to another lecture in the series of Advanced Material and Construction. In the previous lectures, we've discussed polymers on one side and afterwards textiles and their relation to architecture. Today, we're going to combine both and we'll actually talk about composite material, the composition of two elements where 1 + 1 = 3. So what are composite materials? Actually, we know them all along history. I think we've seen this diagram before. So this Ashby diagram traces families of materials across history, and you see that composite materials appear there along with ceramics and polymers from the very early stage, earliest of times. And this is actually the combination that we know in the brick. So we have discussed this. There are the fibers, natural fibers like straw, etc., and they come with mud. Together they form the brick, which is the first maybe industrialized or material design or material science that we know of man. And all along history, there are changes of this combination, but the combination of both actually enables structural elements as the brick. And composite material reappear actually in the 19th century, towards the end of the 19th century and beginning of our 20th century, when we see the combination of reinforced concrete. This is also a composite material. It's a combination of linear element that would take the tensile forces. This is the rebars, the steel, and then there is the cement, the mixture, what we call the matrix, that will hold the things together and will create the reinforced concrete. We saw this towards the end of the lecture on last time. Now, here today we're going to talk about fiber composites. And this is the combination between a polymer matrix and advanced fibers. As we see here, maybe you recognize the black stuff. Well, that's carbon fiber textile, and the polymer that we see, the resin or the matrix, all of them are the same. This is epoxy resin in this case. Now, the combination of both of these two elements that stay distinctly separate, they merge together, and the result is a novel and more useful whole that is a third element that is neither one or the other, but has performance that goes far beyond what each of the elements could achieve separately. Now, the responsibility is shared between the two elements. So on one hand, we have the fibers, which are responsible for carrying the loads and transferring those. These are the elements that would define the strength of the material and define its mechanical properties. On the other hand, we need to stiffen and place these fibers in place, and that's the role of the polymer matrix. So polymer matrix actually transfer, this is the interface between the fibers, each of the fibers, transferring load from one fiber to the other and thereafter to the ground, for example. So not only transferring loads, but also protecting these fibers, and also it affects the material properties, for example, its resistance to various and different factor, and it's a strength or strength with compression. Composite materials are the magic combination between the two constituents, the two elements of fibers and matrix. So on the left, you see different forms of usage of fiber material. All the fibers here are aramid, Kevlar. You recognize those by the yellow color. Nevertheless, you see different forms. So you start from staple. This is a very basic raw on the upper left, short fibers, all the way to roving, which is some kind of a thread or cord. And then afterwards, construction, textile construction, as you would see woven material, knit material, and even braided material. So these varieties and more could be applied to different types of fibers. That's the fiber part. On the right, you have a diagram showing of types of resin that one can use. So most common would be epoxy and polyester. These are widely used in architecture and similar works. But you would also have phenolic resin, polyamide, or cyanotester, all according to the specific performance requirement needed from the finished element. So the combination of both would give you the 1 + 1 = 3. It should be mentioned that here I only put thermoset resin. That's the most commonly used in composite material. However, recent years show that there is a new usage of thermoplastic material in composite And this is mostly used for automotive industry, not so much for architecture for various reasons. So we discuss actually mainly the thermoset resin-based composite. That is a resin that when heated up, after the curing, when heated up, it will not melt or change its shape. Let's have a look on how these raw materials of the composite are made.
We develop and manufacture lightweight, high-strength components for the automotive and aircraft industries. We support the efficient generation of wind energy, and we invest in the future. The material we work with is carbon. The starting material for our lightweight, high-strength components is a precursor based on acrylic fibers. Complex oxidation and carbonization processes convert this precursor into carbon fiber, a unique material used in high-performance textile products and a wide variety of composite materials. SGL Group is the only European-based carbon fiber producer to cover the entire value chain, from fiber to finished component. Our fabrics made from carbon, glass, or aramid fibers can be matched to any particular application and processed further as required. We produce carbon fiber-based multi-axial fabrics for a wide variety of high-quality products. These fabrics allow us to maximize the application-specific stability and stiffness of components while simultaneously saving material. Carbon fiber composite materials open up new applications where other materials reach their limits. Whether fabric designs with variable fiber orientation are required, or different types of weave combined with high-quality resins, we can match our materials ideally to the needs of our customers. Our core competencies cover the production and further processing of carbon fibers, as well as the engineering of carbon fiber composite materials. This leads to technical innovations, such as the automated braiding process. Despite their tremendous strength, carbon fiber reinforced components are less than half the weight of steel and weigh approximately 30% less than aluminum. In automotive engineering, the drastic weight savings achieved with CFRP components not only bring about new performance records, but also reduce both fuel consumption and CO2 emissions. SGL Group supports this innovation by developing processes suitable for large series production in automotive lightweight construction. Complex structural components in carbon fiber composites are indispensable in the manufacture of new generation large capacity aircraft with lower fuel consumption. With our engineering and materials expertise, we are a competent partner for the aircraft industry. We offer our customers tailor-made solutions and set new standards with our automated production processes. The SGL Group invests in future technologies. With our materials and process know-how, we help increase the efficiency of onshore and offshore wind energy plants. In close cooperation with the wind energy industry, we manufacture rotor blades from fiber-reinforced plastics in lengths of 60 meters and more. These blades are used in state-of-the-art wind turbines to ensure maximum safety and low noise levels, combined with high performance and cost-effectiveness. Carbon is the key to innovative, efficient, and sustainable solutions for the environment and our future. Carbon is future. SGL Group, the carbon company.
magical combination of the two gives us a family of material that is very well placed in this Ashby map. So again, mapping density versus strength, and you see that composites, that's the center oval in purple, are placed in a very good place, very near ceramics and steel in the terms of strength, but much lighter, so placed in the middle. And these properties make it very attractive for various applications. Other properties just reinforce that. You see here a comparison between composites as a whole and aluminum and steel as traditional materials. So not only it's much lighter, as we saw in the previous diagram, and it's strong, but also its thermal expansion is minimal. And that means for us architects a very attractive material where radical changes of climate around the building would not cause a large deformation, which of course we would like to prevent. So this and more actually make these composite material, fiber composites, highly attractive to architecture and design. As we see here, maybe the best example of stiffness and strength. You see this diagram of a chair of Shigeru Ban, which is actually a carbon fiber chair, thanks to the properties, the unique properties of the composite material. And these attractive properties are actually present in the consumption that we see just growing and growing across sectors and along the years. So sectors vary, transportation, marine, wind energy, and turbines, and many more. And in yellow, you see here construction. So yes, construction is part of it, and architecture is a segment within construction. And various graphs like those show and demonstrate the growing demand and application of these materials in the past and the recent decades. Here we see an example of Aston Martin, an application in automotive, but there are other brands as well. Or in yachts, it should be mentioned that these materials originate from water, from the sea. They have been applied first in the 1940s for boats, and they still are today. So they're highly resistant to these environmental conditions and suitable to this application of yachts and boats, etc. But not only that, also the performance of the material is highly suitable for sports and other challenging forms or structure where it is required for a certain design, as we see here in product design. The best way to understand to what extent these materials have been embraced and adopted in industry is to have a look in airplanes. This is by all means one of the most conservative industries that we have. Adoption of change is slow, difficult, and nevertheless, you see the adoption of composite material and their usage in aircrafts along the years. And when you board on a plane today, should it be a Dreamliner 787 of Boeing or an Airbus 380, most probably 50% of your aircraft would be composite materials. The rest would be steel and aluminum and titanium, but half of what you see around and what you don't see, the structural elements as well as interiors and decoration, 50% of the materials by weight would be composite materials of various kinds. You see here carbon laminate, carbon sandwich, fiberglass, etc. How about architecture? Well, architects actually have been experimenting and playing around with these materials all along the 20th century, early from the 1930s all the way to the mid-70s. They have been trying quite a few types of polymers, as you see the column here on the right, but mainly, and this is the red line here in the middle, the dense one, experimenting with polyester resin and fiberglass. So that is composite material. And with that, they made pods and pavilions and housing units and experiment in sculptures and whatnot. We already saw the housing of the future, the housing unit of Monsanto House, that is the US in 1957. So with this concept of a future type of housing and a futuristic material came also the concept of modular construction and a flat pack. So in Tomorrowland, because this material is so light and efficient, we can actually manufacture it somewhere, flat pack it, transport it and assemble it on site, and have this minimal volume of transportation in the modular element that we construct. Now, this is taking place in the US, but remember, this is the harsh competition between the Soviet Union and America in those times. So in parallel, there is the Soviet plastic house in 1961. So pretty much the same concept. You see it's elevated from the floor. There is this floating unit, very light, very efficient. And here again, it's made of modules. So these modules, these strips, they can be manufactured and assembled on site. They are extremely efficient, and here again offer maybe a more gentle, but yet again a different kind of aesthetics. Now you see the aesthetics of these two pavilions, these two housing units, and you see the bumping on the left and the curviness on the right. Now there is a reason for that. Since the material is so strong and efficient, well, you don't need a lot of it. It can be very thin. We have very thin layers, very thin membranes or plates. So these membranes, these surfaces, they are strong but not stiff. And for construction, you need to stiffen those. So stiffening strategies are various, but actually one of the stiffening strategies, the main one, would be adding some geometry and curvature to that. So these bumps that you see and the way the windows are sticking out, the openings are sticking out of the panels, or the curved element on the right, all of them actually add structural stability and stiffness to their final result. Actually, stiffening strategies still are used today. Here you see a manual of composite materials and polymers, and you see that actually these pleating, bending, or corrugating the material, adding curvature, actually adds stiffness to the material without adding a lot of mass or matter. Here, again, we see this panelized unit. Now, what's interesting is this concept that not only you have elements that are assembled on site, but these panels actually go all the way from the outer skin to the inside, to the inner part of the unit. So you have the outer skin, then you have isolation and other services going around within in the thickness of this element, and you have the inner skin, which is your interior. So you have one complete element. You can just come and install this. And actually today we are coming back to many of those concepts. We're going to see this in a minute. To conclude, to complete and tie all this up, there is also the design, the environment, or the concept of all plastic. So oftentimes these experiments were also experiments in the language of design that tries to be totalitarian in a way, holistic, if you wish, adopting plastics also for all of the elements here in the bathroom, as we see, and a specific design language which is very colorful and poppy, very typical for those years of the 60s. And we see those atmospheres coming back and again. So here in the Monsanto and in yet another version of it, but still all plastic language, trying to adopt this material in its various forms as in many items as possible. And another example would be the Futuro. So here again, it is marketed and demonstrated with this playful, futuristic family atmosphere. The Futuro house also being based on a modular element, but as opposed to the other example, here we're talking about some kind of blob or sphere, an elliptic alien that has entered a spaceship. And this Futuro actually became a product. So not only marketed as a product, but also appearing in very different areas in Europe. Well, the variation on the left, where the unit itself is inserted in a megastructure, was never realized. There was no Futuro hotel or megastructure, metabolist structure that took those blobs or spheres and insert them as a unit. But variations such as this, the Ventura, combination with aluminum frames and composite material and different geometries, all based on the same idea of a flexibility of assembly and various forms that are suggested here in this system. But the most interesting, maybe, and mind-blowing appearance of these Futuro units is in this slide. Because here comes the idea of transportation, where you can not only manufacture your elements off-site, but also assemble those and transport the unit as a whole, as such, to the location on-site. Thanks to the fact that it is so light, it can be done by air, by crane, or by helicopter. Staying with the crane and this crazy idea that you could just fly around your building or your building element, we jump forward to today. And here, this giant dish is actually Foster & Partners' roof for the auditorium of Apple campus and the headquarters. So this is manufactured in Dubai, assembled on site in the headquarters, lifted in the crane and just placed over the glass perimeter of a wall. So the largest freestanding carbon roof, weighing only 80 tons for a diameter of 46 meters. And this is possible thanks to strength of the material, stiffness by engineering, lightness, of course, and also high accuracy of its fabrication. So fabrication process is highly accurate, and you could be sure that you would have an even positioning of the stresses all around, no concentration of stresses in one part rather than the other that could be harmful for the glass materials supporting this structure. The same principle is what actually enables these huge mashrabiyas of the Apple store of Foster & Partner here in Dubai. And thanks to the dimensional stability, that is the fact that they don't change dimension when temperature is changing, the thermal expansion that we mentioned before. And high accuracy, well, you could have these movable elements 3 stories high that could move around, open and close according to the climate, and also be operated just from the top part of the element, thus preventing all kind of jamming and possible problems for the mechanism to get stuck due to either weather conditions or problems of thermal expansion. Same principle of lightness and accuracy is also what enables the huge wing of the Calatrava structure for the UAE pavilion of the recent expo. So you see here, the mechanism is also very simple and very minimal. You just have these 3 motors that are lifting and closing these elements, the wing of the pavilion. We continue with a few more examples of contemporary applications of fiber composite, demonstrating the unique properties and the opportunities that these bring to the world of architecture. So here with the Stedelijk Museum, its extension in Amsterdam, so the canopy, you see a huge cantilever, very elegant, very thin section, very little material, thanks again to the strength, the lightness, and the stiffness of this engineered material. And the seamless appearance of it is thanks to the finish that they chose, finishing on site, so assembling very large elements that are finished on site, masking actually the seams between the segments, giving you this continuity and this impression of infinite surface floating above. Another property of this material is its ease of adopting complex shape, complex double curved shape, and of course the queen of those is Zaha Hadid. She started already in 2008 experimenting with this Chanel traveling pavilion. It was an art pavilion supposed to travel in 13 countries. So again, a modular construction of light material, actually traveled only to 3 destinations due to the year 2008. Actually, there was an economic crisis and it stopped. Nevertheless, you see a good demonstration of how these materials adopt so nicely complex morphology and double curved surfaces. Zaha Hadid goes on with this masterpiece of the Haidar Aliyev in Baku, and you see the whole building, the whole space is wrapped around with this material, adopting the double curved flowing surfaces that she designs. Here it is actually a combination of two cousin materials. It is GRC, so glass reinforced concrete, and GFRP, glass fiber reinforced polymers. So based on glass fibers with different mixture of cement or polymers, this skin is assembled. You don't see the difference. It is mostly fiber composite FRP, but with some GRC parts in it too. We move to a complete different application. Here it is with the pultrusion or extruded elements in the big Serpentine Pavilion of 2016. So you have these modular elements that are stacked one on top of the other, very light and very stiff, so enabling this mega structure very easily. And on the other hand, as opposed to these rectangular void boxes, we have the complete opposite here by Smiljan Radic, again in the Serpentine Pavilion here in 2014. So this is a very fertile ground for experimentation and demonstration of avant-garde. And here the work of Smiljan Radic, taking the material towards a complete different atmosphere, raw atmosphere, and playing with the translucency of the material, also contrasting between the heavy stones and this almost prehistoric impression upon which has landed this rock or maybe this UFO that is playing around with different texture and sensibilities of the composite material. These contemporary architectural examples and many more just demonstrate the fact that this material family has unique properties that offer advantages to the architectural world, affecting design, fabrication and assembly, and life service as well. Take, for example, the fact that it's so lightweight. For parallel performance, for an equivalent performance, the material could be up to 40% the weight of steel and only 10% the weight of concrete. That means that you can design a slender structure with a tiny section, challenging conditions. And not only that, but its assembly would be affected too, because elements are lighter, it's easier to manipulate, to manhandle, it's safer to install, it's cheaper to helicopter or transport, and so on. And finally, its life service, the fact that it's so resistant to corrosion, the chemical resistant, also means there is a low maintenance and a long life service. This, of course, affects the choice of material over others, and also the way it is implemented within a project. Now, how is it actually done? Well, we know that we need fibers and matrix. These are the two constituents, and we need to combine both. That is, the fibers should be impregnated, fully wetted with the resin. It should be done over a rigid mold. This rigid mold will give it the final shape. So fibers are layered, usually fabric layers, are put on top of each other, and resin is poured or inserted in the fibers. It could be manually, as we see on the top left, on an open mold with a brush or a roller or a spray, and it could be with a double-sided male-female mold. It could be under vacuum pressure. That would be vacuum bagging or resin transfer molding, RTM, or infusion, different names in the industry to indicate that in these kind of processes, the resin is actually impregnated within the material under control of full impregnation and the amount of resin that is within the laminate. That is the composition of the two into a final object. Let's see how this process from mold, layering the material, impregnation, and curing, that is putting in an oven, for example, that could be curing as well. Let's see how this is done in industry. First step would be the fabrication of the mold. There needs to be a shape, a rigid shape. Usually it's milling, it could be in different materials. Finishing of the mold, called fairing, actually involves quite a lot of manual labor to get a perfect finish. The finish of the mold would be the quality of the part that we are manufacturing. fibers are laid up one layer over the other. Here you see the black of carbon. So first carbon fabric layers are stacked. Other layers of fabric could be prepared, for example, glass, and then vacuum is prepared. You see here the resin infusion, the transfer of resin in the part thanks to the vacuum that is affected over the part. The blade here is actually constructed from two elements, two mirroring elements, two parts, and they are bonded together. Then comes the stage of finishing of the part, which is also labor intensive. All the way to the finished part. So that's a turbine blade, but you can imagine with the size, the scale of the element that this could be directly transferred into the world of architecture. It is an architectural scale. With the unique advantages these materials offer to architecture and a fabrication process that is actually suitable to the architectural scale, one can wonder what is the actual share that these materials take in the landscape of construction. Now, compared to the potential to other materials in our sector, they represent only 4%. This is surprising and extremely low. Even when you compare to other sectors, the market penetration is far behind marine, of course, but also transportation, aerospace, and even consumer goods. There is no significant performance gap. So it's not about performance of the material for our architectural requirements. It is slightly due to a price gap. They are still a bit pricey for our sector in comparison to concrete, of course. However, this does not explain fully the only 4% of market penetration. Another cause is probably related to this quote. 40% of the cost of making a panel is just creating the shape. Taking that whole issue of cost out of the equation is a big breakthrough. So not only cost, but also sustainability. The person who is saying that is Bill Chrysler, and he is the manufacturer of this facade that you see here. This is the extension of the MoMA Museum in San Francisco by Snow Hetta, and up to date, this is the largest architectural facade in the US in composite material. Now, why is the shaping so painful to us in architecture? Well, mainly because not only the cost, but our architectural trends are pulling towards complex morphologies and surface articulation. We have the tools, we have the need, and we have the wish, the architectural and aesthetic wish for those, and these complicate all the issue of molds. On top of all that, we would like it to be in high variation, that is non-repetition between the elements. Each element would be different. Again, we have the parametric tools, we have the sustainable need for differentiated elements and facades, and that stands in sharp contrast to the process that we just saw before. So here is the fabrication process of the MoMA facade. You see that very similar to what we saw in the video, from the fabrication of the mold, involving a lot of manual labor, layering the material up to the finished facade. This means that this material, this process, this manual labor is repeated 1,400 times, because each and every element of this facade is different. So not only manual labor and machine labor and cost, but also an extreme material waste. And you see this also in the project that we have here locally. This is the Rabin Center in Tel Aviv. Process is similar. So to manufacture these 400 square meters beautiful wings, the molds are then thrown away and they're not repetitive. Shaping of the composite element in architecture project is therefore a significant barrier. And this barrier is approached in different ways, and we'll see few examples of advanced composite projects in architecture tackling alternative approach of shaping. First would be active bending in the One Ocean Pavilion. And the active bending principle is actually when you apply a pressure on your material, a force on the material, and you bring it to partial failure. So here you see the lateral forces applied on this strip of paper, brings it into buckling. It bends, it does not break, it's not total failure, it still is intact, but it is a partial failure of the material, and that is the required performance. It can be for shape, it could be for stability and stiffness. So through the bending of the material, your structure is actually fully operational and you reach your target. With this inspiration, engineers went into the world of composites. If you remember, composite materials are very strong, but also quite flexible, especially when it concerns glass fibers. So you see here, the element is actually being pushed from its ends, from two ends. With a very slight pressure, you get this buckling and a complex curved surface that is generated. And with this principle, this could be applied to a series of lamella. Each of them would act slightly different. It will also be adaptive to the environment and would open and close according to climate. But most of all, it would not require a specific different mold for each of the lamella, and the shape, the complex shape that is created, can be controlled thanks to the understanding of the process of active bending. Let's have a look of how this is operating and being manufactured. So you see here the gigantic molds, but actually few molds that would be sufficient for all the lamellas of the project. You see the layering of the fibers, glass fibers, over the mold. And according to the material composition, you will have a different structural behavior of each of the elements. That means that it would bend differently according to its stiffness and localized stiffness across the element. From this dynamic behavior of the active bending of the lamella, we go to another dynamic behavior. Here it is the case of cables. This experimental project of Kengo Kuma is for the Komatsu Siren headquarters, and they are manufacturers of fibers, advanced fibers. Here, the whole facade is a second skin that is devised out of cables, carbon fiber cables, and their role is the stabilization, the dynamic stabilization of the building in case of an earthquake. So this secondary skin is actually comprised of these cables, core of a carbon fiber, a sleeve of glass fiber, and this together forms kind of a rope, if you want. These ropes are woven or braided actually in a traditional Japanese braiding technique to make this complex three-dimensional structure, which is actually a rod, a flexible rod. It's equivalent to a steel rod, but it's flexible, it's lighter, and its performance is significant in case of an earthquake. You see here the tensile strength applied to the rods in the event of an earthquake on the X direction and Y direction. The cables go under a tension that is within their structural limits, and therefore it could stabilize the building dynamically in that case for seismic purposes. Staying at the level of the fibers, we have the ongoing experimental work of the ICD in Stuttgart, where they experiment with constructing a structure out of the placing of fibers, direct placing, carbon fiber, the black ones, glass fiber, the white ones. And this is done with a robotic arm in a process called robotic winding. Now, this direct placement of the fibers, even if using jigs as we see here, actually means that you don't need molds anymore for complex shaping of element. So with the same jig here, you would create very different element just by a different winding pattern between the two parts. This not only means that shaping processes affect, but also the structure, its visibility, its aesthetics, and of course, efficient material usage. Oftentimes, the models that they take are from the living world, from biology. They study the way nature organizes fibrous material in space, and with these efficient principles, they are transferred in a biomimetic process from biology through material computation to the world of architecture, where material systems are devised, and all the way to fabrication and assembly. Now, not only this material is very efficient the way it's manufactured, but also the assembly is affected. Such a component weighs even less than 20 kilos, which means that you don't live in a landscape of construction, assembly, fabrication as we know it, but you have components that a single person can lift in a hand, and the whole assembly process is also extremely light, easy, and quick with regards to traditional construction environment that we know. Another example of a filament winding or direct fiber placing is the Dubai Expo portals. The gates of the whole expo were made of this carbon fiber lace, so 21 meter high, 30 meters long, very present, and at the same time extremely airy and light. And thanks to the material properties and the manufacturing process, the result is a structure with high strength, very efficient in terms of material, wind permeable, and bringing shades. But not only that, it is also a strong visual identity of the place with this oriental advanced mashrabiyah in carbon fiber. An evolution of this long experimentation in filament winding in carbon and glass is a switch to a new material, natural fiber composites, which are based on flax fibers. So instead of using glass or carbon, flax fiber is the base of this filament winding, and we see it both in the pavilion of the ICD, the recent one, as well as this railing of a pedestrian bridge in the Netherlands. Of course, more environmentally friendly and sustainable, as these are natural fibers. Their structural mechanical performance is suitable for architectural needs and purposes, and we expect these materials to be more and more present in the landscape of architectural composites. Direct placing actually comes from technologies of advanced sail molding. Let's see how the process is made and how shape is obtained in these complex elements.
Cool. So, well, thanks for letting come by.
Thanks for driving up.
So this is where it all starts, right?
Yep. Just rolls of fiber and barrels of glue, and we turn them into sailboat sails.
Amazing.
Yeah.
It's a bit different to how it used to be.
Yeah, we're in 3DI world now. I mean, and the 3D is kind of the key thing. We mold sails in 3 dimensions, so we get a truer flying shape building them that way. 3DI is tapes, much finer resolution, much higher resolution. We can control where we put the fibers, control the weight, we control anything we want. I mean, the main objective is to make a really durable sail that holds its shape and stays together for as long as the race needs it to stay together.
Whoa, hang on there, Jeff. Let's take this from the top. It all starts here with these barrels of high-tech glue and these rolls of fibre. They get fed into this machine. It's called a pregger. They go in one end and come out the other as rolls of tape that are stored in a pretty unusual place.
So Jeff, this looks like a beer fridge.
In any other sail-off in the world, it would be the best beer fridge in sailmaking, but we're kind of a different sort of place.
So it's cold, and it's in a refrigerator. Why is that?
We only have about 100 hours at ambient temperature to use this and get into a sail before it kicks off.
Oh.
So basically we have to just keep it cool until then. It's the lightest composite tape made because it's 1 filament thick. So we need this machine in order to just get it off the roll and get it down where we want it. There's just nothing to it.
It's just got no substance whatsoever, has it?
Right.
So how many layers of this stuff? Because obviously like that, it's got no strength.
Well, in the corners of the reefs, you could have as many as 60 to 100, depending on the weight of the tape. In the body of the sail, a minimum of 6. Basically, the middle of that sail could be 6 times this thickness. You know, we get a lot of pushback from guys going, wait a minute, my sail's too light, my sail's too thin.
Yeah.
It's like, please go try it, it'll work. And halfway around the world, they say, you're right.
I think I'm starting to get this now. So we make these panels, and I notice those guys over there are rolling them up. Right?
Yeah, they roll them up, put that in a protective canvas bag. We go next door and put it on the molds, and you'll see that in a few minutes.
Roll the panels up. Next door, lay them out on a mold.
Yeah, consolidate them. The way you say it, anybody can do it.
Wow.
Good luck.
Yep. I was wondering what you guys were getting up to up here.
Yeah, not a lot.
So just give me an example of how much tape goes into like one sail, say a mainsail for one of our boats.
A Volvo mainsail with the reefs and everything else, so 20 kilometers, 18 to 22 kilometers.
20 kilometers of tape?
Yeah.
That's amazing.
Once the flat panels are finished, they go next door to be joined up into the full sail that we'll see taking shape for the first time.
So this is the cool stuff. This is the molds, right? The mold tables.
Right.
And which is really at the core of it, of the whole system, really, or one of the key parts, isn't it?
These are 3-dimensionally molded, and it's the only sail in the world. It's the only flexible composite membrane in the world that's molded in 3 dimensions. These molds change infinitely, and they change every single sail. So we make every single sail different, with the exception of a one design class like the Volvo 65, which we are very good at making exactly the same time and time again.
What's actually going on down here?
Well, what this does, this big flexible surface, we try to get the surface as flexible as a sail. It takes the designer's shape that he comes up with through membrane in our software programs and puts it into real shape.
Here, we can see the panels being married together on the moulding table. Next up, a vacuum bag to compress all of the glue evenly throughout the sail.
I'm actually gonna help out here. I'm gonna get stuck in and help.
I think they need your help.
I
Yeah,
can't
exactly.
stand by and watch.
Couldn't do it without you.
Next, for the mould, is the heater, which is used to fully activate the glues and resins. The last job for us today is a thorough inspection, and Jeff explains the next part of the journey for these sails.
So in the case of these sails, the stress analysis of the shape is actually what leads the design of the element. So you have the stress pattern of the sail under performance, and you adapt your material composition and fiber layout to this required performance. So you have one continuous shape that is laid over one large 3-dimensional mold, and fibers are layered accordingly. This leads to a highly efficient performance of the material, highly performative structure of the sail that is designed according to the stress patterns. While not yet applied to architecture, we have 2 examples of the interest that these kind of material could represent. Here in the case of Renzo Piano for Prada, applying these materials as facade elements, I think it's more decorative than anything else. And in the case of Greg Lynn, creating these huge sails for Swarovski as an installation for Design Miami. Although not present in architecture yet, we do have a transfer of knowledge and technology in the flexible mold. So Adapa is a company that creates flexible mold, as we saw for the sails fabrication. These flexible mold get a file, a rhino file for example, and accordingly a surface is organized in space. Actually the pistons are leveled. Each and every panel would have a different configuration and would go directly from the rhino file to the configuration of the mold accordingly. And once you have the shape organized, configured in space, you can fabricate your panel over it. Adapa has been applying this to composite and to concrete elements so far. And specifically interesting for architecture, we have this example of the Museum of the Future in Dubai, where all the facade elements that you see and the internal elements are of different types of fiber composites, and they use adaptive molds. So over the adaptive molds, they even placed these inserts that would create the pattern with a very complex laminate process that you have over the panel, over the mold. You get the panel that is thereafter installed. No molds, just a reconfiguration of a machine. We also had locally the opportunity to experiment with this technology in an R&D project. You see here the configuration of the mold to a required shape. Once the shape is taken in the mold, you can laminate the panel as we showed before. It was interesting to experiment with different materials, all of them different geometry, creating one continuous surface. Carbon fiber on the top right, flax material, glass fiber, and finally fiberglass with a gypsum-based mixture. Based on this prototyping experiment, we could go further for a full-scale architectural project, and it is assembled these days in a pedestrian bridge of 400 square meters that are a non-repetitive complex shape. Together they form this elegant envelope for the steel bridge. And from a machine that serves for the shaping of the element, that is the adaptive mold, we'll move to thinking about the machine for material deposition without the need for a mold, that is 3D printing. Now this is a problem not yet fully resolved in composite materials, since the full capacity of these materials is with a continuous fiber. That is the part that takes the load. That is where the material is in full performance. This is complicated, and that is, say, almost impossible in 3D printing technology as of today. There are some developments interesting to follow of continuous fiber and material deposition. Some other examples exist where fibers are chopped in the mixture, and this is one fine example of the use of this technology on an extremely large scale. I will conclude with a personal project, a life object, Israeli pavilion for the Venice Biennale in Architecture in 2016. And the main installation of the pavilion that you see here was an exploration of alternative modes of fabrication, shaping, assembly of composite architecture inspired by nature. Our starting point, the inspiration, was a bird's nest, this extremely resilient structure made by a bird. So with no scaffolding, machinery, or molds, the bird creates this double curved complex shape with no glue or joints involved. So a complex shape made out of found element, ready-made, that are very light and protective at the same time. And there are embedded details in these elements because there is no joints or glues involved. We took the bird's nest into a scan, a CT scan, and analyzed it algorithmically to understand the principles that lie behind the structure, this efficient structure of the bird's nest. We mapped the distribution of material, element orientation, joint and intersection of the linear elements. And with that, we took this information as the starting point of our design code. So in Grasshopper, we did a random population of linear element in a volume, and this population took as principal the figures that we found in the analysis of the bird's nest. So a distribution, a random distribution of linear element that is based on the structural principles of a bird's nest. A bird's nest is mainly made of twigs, branches, leaves, and straws. That is a natural fiber-based material, fiber composite that are cellulose-based. And we took it to our world of synthetic composites based on fiberglass and aramid fibers. However, we wanted to maintain and keep the same design principle as in natural composites. So forget about molds, complex machinery, or scaffolding, but rather rely on the material capacity for self-organization as we learn from nature. And here you see the fabric, the knit sleeve, that is in tension and creates this shape thanks to the insert, the simple insert that is put in the sleeve that is not only shaping the material, but is also creating some kind of an integrated joint. So from the knitting of the material, very simple fabrication, impregnation, manual impregnation with resin, and then stretching it over the frame, placing the insert wherever we want to create the final shape, and actually allowing for large heterogeneity, endless variations that could be made, thanks to the fact that molds are not involved. It's just about placing these inserts within the different types of sleeves. So together, this formed a double-curved complex volume in space, thanks to a hierarchical construction going all the way from the fiber to the fabric up to the sleeve, and then these elements that are interlaced to form one coherent structure. We finally had two volumes in space together that were about 30 cubic meter that were comprised of 1,500 components, weighing only 150 kilo. These elements were transported flat, so extremely efficient and very light. And if you wonder how come, if they were straight and flat, how come they served and created the shape? Well, the principle that we learned from nature, from the bird, is active bending. That is the slight bending of the linear material, the linear element, to create the final shape. So applying forces on the two ends of the material, a slight bending, partial failure of the material, partial buckling, that will actually bring it to the required performance. In our case, it was not only the bent shape or the double curved shape of the overall element, but also its structural performance. The stability and stiffness of our structure is achieved by the interaction between the bent element, these elements in active bending, applying mutual forces and friction, one element on the other, and together forming this stable structure. Based on previous research, we could learn what are the requirements from this kind of material that could be at the same time resistant enough, but also flexible enough not to break, not to bring us into failure. And with these criteria, we came back to material experimentation, and we found the right and proper mixture of resin that would allow stiffness and strength on one hand, but flexibility on the other, for it to be bent and serve as one element in this structure of active bending. With this final structure of the life object, we'll conclude this chapter of composite material, actually creating the tie between synthetic composite and natural composite. Natural world is going to be the topic of our next lecture. So from synthetic composite material to biological composite. Thank you very much, and see you in the next lecture.